Okay, next we're going to look at y equals tangent pi over 2x. So we know that tangent has vertical asymptotes. So for tangent of x, we know that it has vertical asymptotes at negative pi over 2 and pi over 2. And it's going to look something like this. The period for tangent is going to be pi. So whenever I'm given something in the form of tangent bx, in order to find the period, I take pi and divide it by b. In this case, b is just pi over 2, which is a coefficient of x. So I'm going to take pi and divide it by pi over 2, which is the same thing as multiplying by 2 over pi, and my period is 2. So the way I'm going to graph this is I always want to center it around 0. So think of 0 as like your start place. Now, my period is 2, so that means I'm going to go half of 2 to the right, and that's my asymptote, and half of 2 to the left. So that'd be negative 1 and 1. And notice that this interval from negative 1 to 1 is 2, and that's my period. And then I can graph this the same way. Look something like that. And since my period is 2, it's going to repeat every 2 units. So this will be 3, this will be negative 3, and so on. So the asymptotes occur at odd numbers. So like 1, 3, and 3 plus 2 is 5, 7, etc. And also negative 1, negative 3, etc. So for any odd number, the asymptotes, there are asymptotes in those odd numbers. So we can represent those as 2n minus 1, where n is an integer. And this is where my function, or in this case we said tangent pi over 2x, is not continuous. So it's going to be continuous at all the values except those odd ones. Okay. Next we're going to be looking at tangent, but we're going to have a denominator of x squared plus 1. So it's x tangent x over x squared plus 1. Here I'm going to rewrite this as x times sine x over cosine x divided by x squared plus 1. We know that with fractions, we want to make sure we're not dividing by 0. There are two fractions here. We have the sine over cosine, and then this whole fraction, x over x squared plus 1. So the denominator for sine x over cosine x will be cosine of x, and the denominator of the whole thing will just be x squared plus 1. So we're going to set both of those denominators equal to 0. Well, we know that x squared plus 1 is 0, so x squared is equal to negative 1. And here I'm going to be taking the square root of a negative, which is not possible. So this one will not give us a 0. Next, we look at cosine of x equal to 0. So I'm going to be looking at the unit circle. Cosine equals 0 at pi over 2 and 3 pi over 2. So I'm going to be going back and forth around the circle where pi over 2 and 3 pi over 2 are. And notice the difference between pi over 2 and 3 pi over 2 is just pi. So I can represent this as pi over 2 plus pi k, where k is some integer. So this is where cosine is 0, and cosine is part of the denominator, so this is where it's going to be not continuous. So x tangent x divided by x squared plus 1 is going to be continuous for all x values that are not pi over 2 plus pi k. All right, next we're going to be looking at a square root with a sign. So we'll have square root of x to the fourth plus 1 divided by 1 plus sine squared. We recognize there is a fraction, so we want to set the denominator equal to 0. And here, I'm going to subtract by -1. And when I take the square root, I'm going to be taking a square root of a negative, and I can't do that. So 1 plus sine squared is never going to be 0, so I don't have to worry about that. Now I have to worry about the square root. In general, I know that the square root function looks like this. I cannot take a square root of a negative. And notice there's nothing over here when x is negative. So I want to make sure that whatever is inside the square root will always be greater than or equal to 0. That means x to the fourth must be greater than or equal to -1. And if I take the fourth root, I cannot take the fourth root of a negative number. So this one, I don't have to worry about taking a square root of a negative, since it's always going to be greater than or equal to 0. Okay, and actually it's always going to be greater than or equal to 1, since x to the fourth is going to be greater than or equal to 0, and then if I add 1 to both sides, it's going to be always greater than or equal to 1. So this function does not give us any issues. So we say it's going to be continuous everywhere. Okay. Now let's look at another square root function that might give us some problems. So if we have y is equal to square root 2x plus 3, I want 2x plus 3 to always be greater than or equal to 0. Otherwise, I'm going to be taking a square root of a negative. So I'm going to subtract by 3 and divide by 2. So this is going to be continuous whenever x is greater than or equal to -3/2. And we could represent this in interval notation with a square bracket at -3/2 and then up to infinity. Okay, so by now we should be comfortable with square roots, so let's look at a fourth root. So I take the fourth root of 3x minus 1. Here, because it's even root, the same applies. So I want the inside to be greater than or equal to 0. So for any even root, we're always going to set the inside greater than or equal to 0. For an odd root, I don't care. Odd root is fine. So odd root, it's continuous everywhere, as long as it's not in the denominator or anything crazy like that. But if it was just like y equals an odd root, we're fine. It's continuous everywhere. So here we're going to add 1 to the right, and I'm going to get x is greater than or equal to 1/3. So the interval in which this is continuous is for open bracket at 1/3 all the way up to infinity. Okay. Next we're going to be looking at a cube root. So I have y equals 2x minus 1 to the 1/3. So this is the cube root, and we know we could take the cube root of a negative. So in general, the cube root, it looks something like this. So the domain is all real numbers, so that means it's continuous everywhere. And same thing if we were looking at a fifth root. So if we had y equals 2 minus x to the 1/5 power, because this is a odd root, this is continuous everywhere.